circular orbits, and time dilation. In Newtonian mechanics, when one small mass orbits a very heavy mass, the orbit is a perfect ellipse, the simplest case of which is a perfect circle. In a 43-minute supplementary video, I cover Kepler's laws, elliptical orbits, and the Hohmann transfer orbit to rocket from Earth to Mars. Here we will only look at circular orbits. We'll start with Newtonian circular orbits, and then learn the non-rotating black hole corrections and the time dilation. In space science fiction, sometimes a spaceship is stuck in close orbit around a black hole, and time is frozen aboard the ship while decades or centuries pass for the rest of the universe. We want to see if such a skip to the future is possible or not. I will go through some equations, but don't worry about them. Soon we will learn how black holes make life interesting. The inward centripetal acceleration of the circular motion exactly equals the gravitational acceleration that gives rise to the circular orbit. For circular orbits, an inner orbit has higher angular velocity than an outer orbit, small r, large omega. Angular velocity is inversely proportional to the orbital period. Substituting and rearranging, we get this equation. For circular orbits of small masses around one large mass, widely spaced orbits satisfy that the period squared is proportional to the orbit radius cubed. This is one of Kepler's laws reduced to circular orbits. Angular momentum, L, is the product of orbit radius, the mass of the orbiting body, and its tangential velocity. Angular momentum is a constant of motion in a central force field, even in general relativity, for orbiting a non-rotating black hole. Using several algebra steps, we get an equation that determines the orbital radius from the angular momentum and the masses. We also get the velocity. So, for different circular orbits around a given central mass, velocity and angular velocity decrease with increased orbital radius. They increase with decreasing radius. Angular momentum and period increase with orbital radius. Jupiter has a longer period to orbit the Sun than the Earth's year, which is longer than Mercury's period. Later we will learn about accretion disks feeding black holes and radiating X-rays and visible light. Particles in an accretion disk in circular orbit around a black hole have higher tangential velocity, kinetic energy, and temperature closer in toward the black hole event horizon. For orbital radius equal to the Schwarzschild radius, the Newtonian velocity is 70% of the speed of light, but this needs a general relativity correction. We won't do the work, but the formula relating orbital radius, the reduced circumference, to angular momentum gets modified by general relativity. Here is the equation, one Newtonian, one general relativity for a non-rotating black hole, that determines the circular orbital radius from the angular momentum and the masses. For r much larger than the Schwarzschild radius, the denominator here approaches 1, and the general relativity result approaches the Newtonian result. Angular momentum does not increase uniformly with orbital radius in the general relativity case, different than the Newtonian case. There is an angular momentum minimum at 3 Schwarzschild radii. The minimum is here. It turns out that for r greater than 3 Schwarzschild radius, we have stable circular orbits for matter. So stable orbits are here. Three Schwarzschild radii is the innermost stable circular orbit, the ISCO, for matter orbiting a non-rotating black hole. Later we will see that it is closer in for a rotating black hole. So the ISCO is here. Outside the ISCO, circular orbits are stable. The orbital radius is less than the Newtonian result calculated from angular momentum, so a little closer in than Newtonian, which we won't examine here. In Newtonian gravity, circular orbits are possible arbitrarily close to the surface of a spherical mass, but this is not true with general relativity and compact masses. For r less than 3/2 Schwarzschild radius, an object will spiral in and cross the event horizon unless it rockets away. No circular orbit is possible here for a non-rotating black hole. So this regime here, this is 3/2 Schwarzschild radius, and this regime here, no orbits are possible. We will explore rotating black holes later. For the space between 3/2 and 3 Schwarzschild radii, circular orbits are possible, but they are unstable. If there is a perturbation inward, the object will spiral inward. If there is a perturbation outward, the object will spiral outward. So a spaceship in these unstable orbits would need small station-keeping thrusters to actively maintain the unstable orbit, but they had better not run out of thruster fuel. The ISCO is actually half stable. An outward perturbation will return to the ISCO, but an inward perturbation results in spiraling into the event horizon. The ISCO has the minimum possible value for angular momentum and effective potential energy for any circular orbit. Accretion disk hot matter at the ISCO that loses energy and angular momentum via friction will then spiral into the event horizon, not move into an unstable orbit. Now let's look at orbital speed. For a shell observer at the same radius, r coordinate, as the circularly orbiting object, the shell observer will measure the orbiting object's speed as this value, which is larger than the Newtonian speed would be. A theoretical shell observer sees the orbiting object's speed as 1/2 the speed of light at the ISCO and approach the speed of light at 3/2 Schwarzschild radius, the lower bound for unstable circular orbits. Light can orbit the black hole circularly at 3/2 Schwarzschild radius. This light orbit is called the photon sphere, or the ring of fire, or the last photon orbit. This is the only radius at which light can orbit circularly. These light orbits are unstable. These photons will eventually either escape to the outside or spiral in toward the event horizon. We will see later that with the curvature of spacetime, photons that escape outward from the ring of fire will appear to a distant observer as coming from a ring at 2.6 Schwarzschild radii, close to the ISCO. Looking across this volume, we do not see the stars behind the volume. This is the black hole shadow. This is larger than the event horizon and larger than the calculated ring of fire. More on the shadow later. A plunging observer can still emit light radially outward from between the ring of fire and the event horizon. Now let's look at time dilation. The faraway observer sees the orbiting observer's clock run slow, as does the shell observer at the same radius. I believe that the time dilation for the faraway observer is this formula, which I'm graphing here. This time dilation approaches infinity as r approaches 3/2 Schwarzschild radii, the lower bound for unstable circular orbits. Time dilation is higher, closer to the central mass. In part due to this, a Newtonian elliptical orbit gets perturbed. General relativity causes elliptical orbits to precess. In our solar system, elliptical orbits of the planets also precess due to the planets' mutual gravitational attraction. I cover this in the supplementary video. In the main course, we will only cover circular orbits. Sometimes science fiction needs to achieve a large time dilation, but the orbit must be a stable orbit, not unstable. The spaceship might be drifting, as in the television show Andromeda from 2000, or the orbiting object might be a planet, as in the movie Interstellar from 2014. Later in this course, we will try to understand some of the effects from the movie Interstellar and learn where the movie exaggerated, pushed the limits, or was impossible. If you have not seen the movie, you might want to see it, if only for the visual effects and the time dilation, but don't believe everything in the movie. For a non-rotating black hole, the largest time dilation, and consequently gravitational redshift, that can be achieved with a stable circular orbit is 1.4 at the ISCO. Later we will see that time dilation can be higher for a rotating black hole. This time dilation for the non-rotating black hole ISCO is not very large for a planet or drifting spaceship, but our active spaceship can do better with an unstable orbit. Let's find the largest time dilations for the closest circular orbits that humans could survive for a non-rotating black hole. The tidal force is higher for an orbiting observer than for a plunging observer at the same radius. I believe that this is that correct ratio. This tidal force for an orbiting observer approaches infinity as r approaches 3/2 Schwarzschild radius, which makes this denominator go to 0. The lower bound for unstable circular orbits. But the tidal force is at most 50% excess for stable circular orbits. I have calculated the closest orbits, stable or unstable, that a human can survive tidally and the time dilation at those orbits. A human observer starts to feel tidally uncomfortable 320 radii from a neutron star and 210 Schwarzschild radii from a 10 solar mass black hole. At those standoff distances, the time dilation for the neutron star or stellar mass is way too small to serve as good science fiction portals to the future. We're going to need a supermassive black hole, where an orbiting observer can survive close to the inner limit for unstable circular orbits. For a non-rotating supermassive black hole, there is an unstable orbit that does not require an energy boost or reduction from the faraway rest mass energy, and so is energetically easy for a spaceship to enter this orbit. This occurs at twice the Schwarzschild radius and has a time dilation factor of 2. Not good enough for a portal to the future. To really actively escape the present, hide out, and emerge in the universe's future, using a non-rotating or slowly rotating supermassive black hole, science fiction could choose an unstable orbit using station-keeping thrusters as close to 1.5 Schwarzschild radii of a non-rotating supermassive black hole as we can survive, which turns out to be pretty close. The idea is to get this denominator close to 0, so the faraway time gets very large. The Milky Way supermassive black hole is rotating slowly, but even if it were not, a human observer could theoretically safely orbit so close, this distance, that time dilation and gravitational redshift would be 364. Time passes 364 times faster for the faraway observer and the Earth than for our orbiting observer. 1 day for the astronaut would be 1 year on Earth. They could actively orbit for a year of their time and then deorbit into the universe that has aged 364 years. A nice bit of one-directional time travel for space science fiction shows and movies. Although a human could survive that close-in orbit tidally, unfortunately it is energetically impractical to reach that orbit using rocket thrust. The spaceship energy would have to be boosted to more than 120 times its rest mass energy for that orbit. Darn, that's impractical even for science fiction. Also, that unstable orbit might be too close in for a huge rocket ship to survive tidally, though a human or a small shuttlecraft would survive. In a 30-minute supplementary video, I cover the effective potential energy curves to orbit a non-rotating black hole and the energies required for orbits. For a 1 billion solar mass, non-rotating supermassive black hole in some other galaxy, a human observer could theoretically orbit so close to the limit that 10 years pass in the universe for every hour spent on orbit. You could travel 88,000 years forward for each year of active orbiting. However, to reach this orbit, the spaceship energy would have to be boosted to 30,000 times its rest mass energy. Ridiculous, even for science fiction. All this ignores an accretion disk you might slam into and be destroyed, and any radiation that might kill you and destroy your ship. And alas, there is no warp drive or wormhole to take us to a supermassive black hole. Energy and angular momentum per unit mass are constants of motion around a non-rotating black hole, as they are in Newtonian mechanics, but not so for a rotating black hole, as we will see later. We have completed learning about shell observers, plunging observers, and orbiting observers for a non-rotating black hole. Let's recap where human shell observers and orbiting observers can survive near the black hole. I will quote what would kill an astronaut in a spaceship outside, an astronaut in a spacesuit outside a spaceship. It would be a different value for crushing the spaceship. At the same point in space and time, shell observers, plunging observers, and circularly orbiting observers experience spacetime differently. Different passage of time, time dilation and gravitational redshift between observers, different space curvature, different tidal force or acceleration. This is confusing to our everyday experience and intuition. We have to trust the results from some physics source that solves special cases with care. If we try to generalize to other situations, we could be wrong either a little or a lot. For example, we're not covering elliptical orbits at all. Plunging and orbiting observers are in free fall, so do not feel ordinary gravitational force on their bodies or spaceships. They're weightless. But a shell observer experiences gravity and weight. Being too close to the event horizon would kill a human shell observer without killing a plunging observer or an orbiting observer in an allowed orbit. Ordinary gravity would be higher than 7 Gs and kill a human shell observer at 231 Schwarzschild radii for the Milky Way supermassive black hole. Hypothetical shell observers are possible down to the event horizon, closer in than the ISCO or the Ring of Fire, but human shell observers cannot survive that close to the Milky Way supermassive black hole. But for a 66 billion solar mass supermassive black hole in another galaxy, the human shell observer could survive gravity down to 2.15 Schwarzschild radii, inside the ISCO, but outside the Ring of Fire. Tidal force, tidal acceleration, is small for a shell observer or plunging observer outside the event horizon for a supermassive black hole, not so for a stellar mass black hole. But for a circularly orbiting observer, tidal force increases to infinity for orbits approaching 1.5 Schwarzschild radii, the innermost unstable circular orbit for a spaceship, not for accretion disk material. An orbiting observer can survive tidal acceleration down to 1.50011 Schwarzschild radii for the Milky Way supermassive black hole, close to the Ring of Fire. For a 10 solar mass black hole, the human orbiting observer needs to stay at least 207 Schwarzschild radii due to tidal force, whereas a human shell observer would have to be 150,000 Schwarzschild radii due to the ordinary strength of gravity. This completes circular orbits of non-rotating black holes. Gravitational waves and merging black holes. When I toss a ball from one hand to the other, the universe needs to know that the ball has accelerated and moved so that gravitational attraction to the ball points in the correct direction with the correct magnitude. Likewise, for every instant the moon moves in its orbit of the Earth, and the Earth moves in its orbit of the Sun, etc. Newtonian gravitational interactions have always been treated as actions at a distance, thought of as propagating instantaneously to the entire universe. But special relativity says that no information can travel faster than the speed of light in vacuum. General relativity says that gravitational information about accelerations of masses propagates outward as gravitational waves that radiate outward at the speed of light to the entire universe. When a spherically symmetrical mass distribution either explodes symmetrically or collapses symmetrically, this does not produce gravitational radiation. Gravitational forces already know how to point to the center of the mass distribution. When a mass has been undergoing linear motion at constant speed, there is no acceleration, and this does not produce gravitational radiation. But when masses are accelerated, gravitational waves get radiated to the universe. Gravitational waves have energy, so the accelerated mass loses energy at a slow rate, with the total energy being conserved. We can think of this as an energy tax or penalty for accelerated motion. This is somewhat analogous to classical friction and viscosity, but a different mechanism and effect. Later, we will see how a gravitational wave presents as it passes through the Earth. For a pair of stars orbiting one another, and therefore accelerating, gravitational wave amplitude is extremely small, far from the stars. However, in 2015, the Laser Interferometry Gravitational Wave Observatories, LIGO, directly measured gravitational waves radiating from the final second of the merging of two stellar mass black holes 1.3 billion light years away 1.3 billion years ago. Let's look at a simulation. The two black dots are the two black holes. The video will shortly zoom in closer. The shades of blue are representing the peaks and valleys of the radiated gravitational waves. Later, purple and pink will be added when the waves have higher intensity. The green, yellow, and red are representing the gravitational potentials. So they're showing multiple things on the same animation. Here is the countdown clock. This is the final 3/4 of a second before the two black holes merge. The beginning of the simulation is about 60 times slower than real time, and then it slows down even more. The gravitational wave amplitude is shown at the bottom. It's difficult to see, but the amplitude graph will get colored blue to show the moment of the animation. Now I'm going to start the animation. So here we have a half second to go. We see the black holes. This is the gravitational potentials. These arrows are gravitational force pointing into the wells. And the blue gravitational waves are propagating outward. Now the animation is slowing down for us. Here we have 3 milliseconds to go. The gravitational waves have increased in frequency and amplitude and are now shown in pink. Now the movie is frozen. The animation is frozen. Now the black holes have merged. And in a few milliseconds, the merged black hole is rapidly settling down to be spherically symmetrical. That highly energetic event was the inward spiral and merging of a pair of black holes with masses of 35 and 30 solar masses, creating one rotating black hole of 62 solar masses, not 65, and radiating away 3 solar masses of rest mass energy as gravitational waves, 1,000 times more radiated energy than the brightest supernova. In the final 20 milliseconds of the merging, the black hole pair radiated 50 times more power in gravitational radiation than the combined power of all light radiated by all the stars in the observable universe. And this was 2 stellar mass black holes. Imagine the energy of 2 supermassive black holes merging. There's nothing unusual with a bound system mass energy being less than the sum of the constituent mass energies isolated far from one another. This is the binding energy and happens with nuclei, atoms, molecules, planets, stars, and astronomical orbits. For nuclei, physicists even use the term mass defect for the binding energy. When atoms or subatomic particles settle into a bound state, the binding energy is typically radiated away as electromagnetic radiation. The total energy is conserved when we include the radiated energy. What is unusual about this black hole merging is that the mass energy that we have previously said is located inside the event horizons seems to reduce, and yet we have said many times that no matter or light inside the event horizon can ever escape into our universe. So, is this an exception, or what is going on here? No matter or energy gets emitted by the singularities, nor outward across the event horizons, but we need to learn a new perspective. There are two explanations. First, let's look at a semi-classical explanation, which applies until about 20 milliseconds before this black hole merging, and does not depend on the objects being black holes. In the Newtonian case of a decaying orbit, say due to friction with an atmosphere, like a spacecraft returning to Earth, kinetic energy gets continuously radiated away as heat and light due to friction. This reduces the orbital radius, which makes the gravitational potential energy more negative, which increases the kinetic energy, and binding gets stronger. Even without friction, the circular motion of the mass is acceleration, and general relativity continuously converts some of the orbital kinetic energy into gravitational radiation. This is the source of the sinusoidal gravitational waves for two stellar mass black holes until about 20 milliseconds before they merge. For the final 20 milliseconds, we need the second general relativistic way to look at this situation. The details of mass and energy inside the event horizon are not available to us outside the event horizon, even though general relativity applies. The total mass energy of the isolated black hole dictates its Schwarzschild radius. We can imagine that the value for the mass energy gets frozen into the external gravitational potential, the spacetime stress energy, and the event horizon, which gets larger as more mass energy crosses the event horizon inward. We cannot observe the internals from the outside, and we don't even have a good theory of mass energy at the singularity. So, we should stop thinking of the mass energy as collected at the singularity, where we might possibly go in and count it. Instead, we should think of the Schwarzschild radius as the count of mass energy as far as our universe is concerned, and the event horizon and the external gravitational potential as the only source of information available to us. As two black holes orbit one another closely before merging, their event horizons deform and flex. We will see another simulation in a minute. The deformation of the event horizons and the external gravitational potential radiates gravitational waves to the universe. We should think of the energy for the gravitational waves as coming from the changing deformation of the external gravitational potential. But the event horizon is easier to visualize. So, physicists say the black hole loses mass energy due to deformation of the external gravitational potential. They say we should not ponder over the mass energy inside the event horizon, which we cannot go measure and is lost to our universe. However, neither matter nor light escape the event horizon to get converted into gravitational waves. There will also be gravitational waves inside the event horizons and gravitational waves that cross into the event horizons. But these don't escape across the event horizon, and we will ignore them. Let's look at a second simulation, looking from above, this time also simulating the gravitational lensing of imagined background stars in that distant galaxy, which, though impressive, we will ignore. This animation starts at 1/3 of a second before the merging. First, let's watch the video. I think this simulation is about 80 times slower than real time. The black areas here are not the event horizons, but the black hole shadows surrounding the event horizons, about 2.6 times the size of the event horizons within them. The black hole shadows are due to the bending of light, due to the curvature of spacetime, as we will learn later. The event horizons and black hole shadows both flex and bulge, so we will use the black hole shadow as a proxy for the unseen event horizons. In this section, I want to talk about the physics of the event horizons, though it is the black hole shadows that we see in the animation. Now let me draw the initial black hole shadows. Now let me draw the initial black hole shadows. Now let me draw the black hole shadows 4 cycles later, about 2/10 of a second later, about 1 cycle before the merging. Note how the black hole shadows have flexed and bulged. From this you can imagine the deformation of the external gravitational potential, which powers the gravitational radiation. Shortly after the two black hole shadows touch, there will be a single extremely deformed event horizon, which rapidly snaps back to spherical shape. In that process, the final external gravitational potential and event horizon have lost significant mass energy, which has been radiated away as gravitational waves. Total energy on our side of the event horizon is conserved when we include the radiated energy and assign the gravitational potential energy as the mass energy of the black hole. We cannot see into the internals of the black hole, and we must give up thinking that the amount of mass energy apparent from the Schwarzschild radius and external measurables equals the amount of mass energy that plunged into the event singularity, which we cannot measure. So do not think that mass energy was ejected from the singularity or the event horizon to power the gravitational waves and reduce the mass of the black hole. Since mass energy was lost in the merging, the final Schwarzschild radius is less than the sum of the two initial Schwarzschild radii. However, physicists believe that the final event horizon area, proportional to radius squared, is always at least the sum of the two initial event horizon areas. This limits the fraction of mass energy that can be radiated away to 29% of the sum, which is a huge conversion, much more than any fusion process. This particular merging radiated away 4.6% of the sum mass energy, and the final black hole's radius is 4.6% smaller than the sum of the initial radii. If the two masses had differed greatly, nearly all of the smaller black hole's mass energy could potentially get radiated away, unless there's other limits that I'm not aware of. Physicists assign an entropy or information content to a black hole proportional to the area of the event horizon. This resolves an issue in thermodynamics of entropy otherwise disappearing as matter crosses the event horizon. For the merging black holes, the final event horizon area will be at least the sum of the initial areas, and entropy does not decrease with the merging. You might also see the term holographic principle. I have not studied these aspects of black holes. You can find more information on the Wikipedia page, Black Hole Thermodynamics. The two black holes had been orbiting one another as a close binary system, about 20 revolutions per second, 50 millisecond period, separated by about 1,000 kilometers, about 10 Schwarzschild radii. Orbital speed about half the speed of light. As they orbited one another, they continuously radiated gravitational waves to the universe, of wavelength around 7,500 kilometers, larger than the binary system. The gravitational waves carry away energy as well as information about the black hole's positions. The energy lost as gravitational waves caused the black holes to spiral in closer together as they orbited, increasing their orbital speed, reducing their orbital period, and radiating even stronger gravitational waves at shorter wavelengths. Notice, however, it only takes a few milliseconds to ring down after the event horizons touch, and how still everything looks a tenth of a second after the merging. Here are the actual LIGO signals. Over 5 orbits, their orbital period decreased to about 13 milliseconds, and a separation of about 350 kilometers, about 3 Schwarzschild radii. The orbits are described by modified Newtonian mechanics up to this point. In the next 20 milliseconds, the event horizons touched and merged into a combined non-spherical, rapidly rotating event horizon, and then rapidly vibrated, rang down, to become spherical, radiating away all evidence other than its rotation of its past being two separate masses. Close to the merger of two compact objects, black holes or neutron stars, the tidal accelerations, due to the gravitational waves, are immense, complicated, and lethal. Far from the merger, the gravitational wave is a transverse wave of strain to the curvature of spacetime. Alternate circumferential tidal accelerations, perpendicular to the radial propagation through space, per this animation, which is greatly exaggerated to show the effect. The propagation direction is perpendicular to this plane, out from the board toward you. As a gravitational wave passes through the Earth, space is repeatedly, alternately, stretched and compressed tidally, perpendicular to the wave propagation direction, by an extremely small amount, smaller than the size of a proton. One direction is stretched while the other direction is compressed, and then they switch. This is a transverse wave. For two objects orbiting one another stably, this radiated wave can persist for millions or billions of years at low amplitude. However, when two compact objects spiral in and merge into a black hole, there can be tens of cycles of higher amplitude while the two masses are merging, and that is what LIGO can detect. This infinitesimal stretch and compression have no effect on living organisms and structures far from the merger. It's very impressive and hard to believe, really, that experimental physicists are able to measure these gravitational waves at all by using freely floating test masses in 4-kilometer-long vacuum cavities, using interference of laser light that has been quantum mechanically squeezed to reduce the quantum uncertainty in wavelength and position. Gravitational waves propagate along the same geodesic trajectories as light waves. Time dilation, gravitational redshift, and gravitational lensing apply to gravitational waves as well as light waves. General relativity is a classical, not quantum mechanical theory. Physicists believe that gravitational waves are probably quantized, and the presumed force-mediating particle is named the graviton, a spin-2 boson. However, physicists do not have a testable theory of quantum gravity, and gravitons are beyond our current ability to detect. Here is a chart of about 50 mergers, two compact bodies merging into one, that have been detected by LIGO so far. The vertical axis is mass in solar masses. Blue circles at the top of the image are stellar mass black holes. Orange circles at the bottom of the image are neutron stars. Physicists are trying to determine the mass threshold between neutron stars and stellar mass black holes, somewhere between 2 and 3 solar masses, perhaps around 2.1. These points are shown as white circles in the middle of the image. When two astronomical compact objects orbit one another and then spiral in and merge, the resulting object rotates, unlike the simplified non-rotating Schwarzschild black hole that we have treated so far. When two black holes merge, the area of the final event horizon is always at least as large as the sum of the areas of the original event horizons. Presently, physicists are only able to detect mergers of two stellar mass black holes or neutron stars. Physicists would like to build additional instruments on Earth and in space with different frequency ranges and sensitivities to detect stars being swallowed by supermassive black holes, or two supermassive black holes merging, or gravitational phenomena from the beginning of our observable universe. The merger of two black holes does not emit any light if they don't have accretion disks. But if one or both of the objects are neutron stars, then gamma rays and light would be emitted in addition to the gravitational radiation. Physicists now believe that many heavy nuclei in the universe and on Earth, such as silver, gold, platinum, iodine, and uranium, were produced largely as high-speed ejecta of neutron star mergers. Every binary system, with both objects orbiting the system's center of mass, loses energy over time as it radiates gravitational waves. The two objects slowly move closer to one another and orbit more rapidly. This has been detected by astronomers. Gravitational lensing, small deflections. Using general relativity, Einstein predicted that the sun's mass acts as an optical lens, bending light rays around its edge. Einstein predicted that stars slightly behind the sun might be seen as being at the sun's limb, deflected by 1.7 arc seconds, 1,000th of the sun's angular diameter. So the star is here, its light passes close to the sun, it gets deflected, we see it on Earth, but we think that the star is there. This is greatly exaggerated. The image is greatly exaggerated. This is twice the value one would get using Newtonian mechanics if light consisted of particles with mass, which it does not. Einstein's prediction was confirmed experimentally by Arthur Eddington during the total solar eclipse of 1919, which made Einstein an instant celebrity, despite his German heritage and it being just after the devastating World War I. The factor of 2 between the Newtonian prediction and the general relativity prediction is not arbitrary. The additional equal component comes from the curvature of space. Gravitational lensing concentrates the background light, radio waves, X-rays, and even gravitational waves from a background galaxy or star distantly behind a massive structure, typically a galaxy or cluster of galaxies, and can yield multiple images, arcs or rings from a single background object. The representation on the left shows how the observer, here, can see a doubled image, here and here, of the background source, here. Here is a massive object. This light trajectory from this source gets bent into this trajectory and seen by the observer, who thinks the source is over there. This light trajectory is a little further from the massive object, and it gets bent less, but still bent, and the observer sees it here. The image on the right shows multiple partial Einstein rings for the two background sources, galaxies, in addition to the foreground galaxy in the center. So, this is the foreground galaxy, which has a lot of mass, and there are two galaxies behind it. The light from one of them is this partial ring and this partial ring, which are white, and there is another galaxy more distant whose light gets bent into this blue ring and here and here. A glass convex lens magnifies an image because light takes longer to pass through the thick center of the lens than through the thinner edges of the lens, such that multiple paths reach the focus at the same time. Gravitational lensing magnifies a background image because background light takes longer to pass through the highly curved space close to the center of the massive object than through the less curved space further away. Since 1979, gravitational lensing has grown to become a major tool of modern astronomy. Most useful is where the massive structure is a massive galaxy or cluster of galaxies, not a single star or black hole. And the distant background galaxy or quasar is twice as far from us as the foreground gravitating structure. This gives the best magnification. The gravitational lens magnifies very distant, very old galaxies that otherwise would be too dim to be seen. It is helpful to astronomers that all wavelengths of electromagnetic radiation get lensed equally. Gravitational lensing allowed astronomers to see the light emitted from an individual, very distant star over 12 billion years ago, 900 million years after the Big Bang. Gravitational lensing can also be used to calculate the mass of the foreground galaxy or galaxy clusters, i.e., to weigh it. Most of this mass will be dark matter, whose mass contributes to gravitational lensing as well as ordinary matter mass. Gravitational lensing can be analyzed to determine the mass distribution of the foreground object. Gravitational microlensing looks not for images, but for small changes of background brightness over time due to a moving foreground mass, for example, a stellar mass black hole, which might be unseen. Microlensing has been used to attempt to detect, unsuccessfully to date, dark matter candidates called massive compact halo objects, or MACHOs, and primordial black holes.